Ben ritrovati. So, from this lecture until the end of this course, we will focus on the applications of cold atoms. And the first application that I would like to discuss is the realization of ultra-cold quantum gases. So we will speak about Bose-Einstein condensates and atomic Fermi gases. And I've already shown you this slide, and so you see from this energy diagram that Bose-Einstein condensate and Fermi gases are of cold atoms are the coldest form of matter that you can achieve on the Earth, and also most arguably in the universe. And so today we would like to start the discussion with Bose-Einstein condensate, and so we will see what they are, how we can produce them, and you will see that this topic is very much connected to the evaporative cooling that we mentioned in the last lecture. And so what they can be used for, and so on. So this is an introduction to the topic of quantum gases, and of course we will spend just 2 or 3 lectures to them. So I just touch the point of the physics that you can discuss with these systems, and of course, if you are interested, there is a more specialized course on ultra-cold quantum gases. That is the course taught by Giovanni Modugno and Marco Fattori. So there you can learn about all the different aspects of the physics of quantum gases that you can study with cold atoms. And of course, this is also a topic that is very important for the research activity in the Department of Physics and also here in Florence at Lens. Okay, so let's start with a discussion of Bose-Einstein condensates, and let's start with just a very short review on quantum gases. So I know that you have already studied quantum gases in the course by Alessandro Cuccoli, and but anyway, I would like to review just the basics. And in particular, I will focus the discussion on the behavior of quantum gases trapped in harmonic traps, because this is the system that we realize in the experiment. So we don't have Bose-Einstein condensation in free space, as that you have studied, but Bose-Einstein condensation of a gas that is trapped in either a magnetic trap or an optical dipole trap. So we will review the basics of quantum gases and Bose-Einstein condensation and Fermi gases in the case of harmonic trapping. So let's start with this introduction. And so we consider a gas that is trapped in harmonic potential. And you know that the form of potential determines the energy levels, and in the case of a harmonic potential, you have equispaced energy levels. So this situation that we can create in the experiment is very easy also from the point of view of theoretical modeling of a problem, because of this simple energy spectrum. Since we are going to discuss quantum gases, of course, we should consider identical particles. And last time we have reviewed the physics of a classical gas, of particles that are trapped in this harmonic potential. And so we have reviewed the Maxwell-Boltzmann distribution, and I can write it again. So the Maxwell-Boltzmann distribution tells you that occupancy of the energy levels is given by the exponential of the energy, written in this form, where beta is the inverse temperature and mu is the chemical potential. And we can treat this gas as a classical gas when basically the occupation number, so this quantity n as a function of epsilon, is much less than 1 for all the possible energies in the system. So if n of epsilon is much less than 1, for every value of epsilon. So this means basically that your levels are almost empty. So the probability of occupying a level is very small, and so the situation will be something like this. So you'll have just a few particles compared to the energy levels that are available. And so basically the probability of occupation of the same level by 2 particles is very small. So this configuration is very unlikely. And for this reason, even if you have identical particles, so basically the effects of quantum statistics do not play any role in this regime of small occupancies. So this is a classical gas, and we can recast this condition on the classicality of the gas also in other terms. So I will now review an important quantity that is a way of quantifying the level of degeneracy of a gas. And in order to do that, let me take the equations that I wrote in the last lecture about the quantum statistics of a classical gas. In the last lecture, we have reviewed an important concept that is the phase space density. So let me take the equations that we have discussed together. So these are the two relevant equations for the phase space density and also for the real space density. So let me now take rho 0 and n 0 and divide one by each other. So let me calculate rho 0, that is the maximum phase space density in the center of a trap, divided by the maximum density again in the center of a trap. So I just need to take these expressions, and so calculation is easy, just a few passages. So rho 0 is n times beta to the third, omega to the third, divided by 2 pi to the third. Good, divided by the peak density, and so we have 1 divided by n. And so I will use this expression, and we have beta to the 3 half, m to the 3 half, omega to the third, and 2 pi to the 3 half. Okay, so let's simplify things. For example, we can simplify the number of particles, and we can simplify also the frequency. And so we are left with 1 divided by 2 pi to the 3 half. Then we have the mass to the 3 half. And then we have beta, that is 1 divided by kT. And so we can write these as kBt to the 3 half. And so we can now define a quantity that you already know, but let's review the definition, that is the de Broglie thermal wavelength. That is a quantity that is defined as, so you can find different definitions that that can be different just by some prefactors on the order of 1. So the definition that I will use is the definition of a de Broglie wavelength as the Planck constant, h, divided by the square root of 2 pi mass Boltzmann constant times the temperature. And you know that this quantity is a measure of the wave-like behavior of your particles. So this quantity depends on the temperature, and if we recall the definition of a temperature in terms of the variance of the momentum of the particles in your gas, so you realize that this quantity is basically the de Broglie wavelength that is associated to the root mean square value of the momentum. And so this gives you an idea of a typical coherence length of your particles. So it sets the scale, so the length over which your particles in average will show a wave-like behavior. So of course the momenta of different particles will be different, but they will have some uncertainty that is given by this variance in the momentum. And so this is the length scale which is associated to this momentum scale. So we can picture this de Broglie wavelength in this way. So if we have a gas of particles, each of them has a quantum mechanical wave function associated, and we can think to this thermal de Broglie wavelength as the typical extension of these wave packets. So let's see how this quantity enters the expression for the phase space density here above. And of course, these will be given by lambda de Broglie to the cube divided by Planck constant to the cube. And so if we now rewrite this expression in a more compact way, we realize that this can be written as rho 0 times h cube equal n0 lambda de Broglie to the cube. So what is the meaning of this expression? So in particular, what is the meaning of what you have at the left-hand side? So this quantity is basically the phase space density in the center of a trap times h cube, that is the size, that is the volume of an elementary cell in phase space. So h cube, you know that in the quantum description of phase space, gives you the volume of uncertainty that is associated to the Heisenberg uncertainty principle. So you can think to a partition of phase space in many cells of volume h cube. And so basically, when this number that is circled here is much less than 1, so your gas is a classical gas, because the probability of having two particles in the same unit cell in phase space is much lower than 1. And so in this case, you can treat your gas as a classical gas, and so this is a different way of recasting this classicality criterion that we have expressed before. So this quantity should be much less than 1. And so we can refer to this quantity as the degeneracy parameter. When it is much less than 1, you have a classical gas. When it is on the order of 1, you need to consider quantum statistics. And we can also write it in a different form by recalling that the density is associated to the average distance between the particles, that we can call, for example, A or D. Let me call it D. And so we can write that this is lambda de Broglie divided by D to the cube. Okay, and so now the interpretation of this criterion is clear. So you have a classical gas when the de Broglie wavelength is much smaller than the average distance between the particles. And so this is what happens, for example, in this graphical representation here. And so this quantity is what we have defined as D. And so this D is larger, much larger than the size, than the length over which the particles exhibit a wave-like behavior. And of course, the quantum gas, you get a quantum gas when either you increase the density, and so you make these particles closer one to each other, and so when they get closer, basically the D can be on the same order of the de Broglie wavelength, and so you need to consider the interference of a wave function that are associated to these identical particles. And so we will have the effects that we will review in a moment. Or you can get that when you increase the temperature, when you decrease the temperature. And of course, when you decrease the temperature, you can make this de Broglie wavelength larger. And so you can also reach this regime in which these wave packets will start to overlap one with each other. Okay, so let's go back to the previous slide. So this is the criterion that we have derived. And I apologize for using the same symbol both for the density real space and for the average occupation number, but I hope that will be clear from the context which of the two meanings has to be considered. Now, if we want to make our classical gas more quantum, we have to do two things. Either, we have said, you increase the density, or you decrease the temperature. And in both cases, you can arrive to a situation in which the possibility of occupation of the same state by two particles must be considered. And so you know that things are different whether you have bosons or fermions. And so you have the two quantum statistics that are the Bose-Einstein statistics and the Fermi-Dirac statistics, that differ from this -1 or +1 sign in the mean occupation number. And you know that this minus or plus makes the physics completely different in the low temperature limit. So let's review what happens at T0. So at temperature 0, so the behavior is remarkably different. And so in the case of bosons, you can have the occupation of ground state by all the particles. And so you will have all the particles occupying the same ground state. And these can be done without problems because bosons like to be together, and so because of the symmetry of a many-body wave function, they can occupy the same ground state. In the case of Fermi-Dirac, the situation is different because the symmetrization of a wave function forbids the occupancy of two particles of the same level by two particles. And here we are considering identical particles with no spin. So we don't have any additional degree of freedom that can distinguish between the particles. And so if you are considering a spinless gas of fermions, so at T0, you will form a nice Fermi gas in which all the particles will occupy the levels up to some Fermi energy. That is the maximum energy that is allowed by the filling of the states. Okay, so this of course is what happens at T0. And yeah, in this case, of course, you have an occupancy that is not much less than 1. So in the case of Fermi-Dirac, it is at most 1. And in the case of Bose-Einstein condensate, for the ground state can be even much larger than 1 for at least some states. So this T0, if you go to a finite value of the temperature, of course you will have thermal occupation of higher levels. And so in the case of a Fermi-Dirac distribution, you will dig some holes in this Fermi sea, and so you will have some population of states above the Fermi energy, something like this. In the case of Bose-Einstein statistics, so you will have some population of the excited states as well. But the nice thing about Bose-Einstein statistics that you have already studied and we will review in a few minutes is Bose-Einstein condensation. So the fact that you have a phase transition, and so there is a critical temperature for which you will start to have a macroscopic occupancy of the ground state by the particles in your gas. So in some sense, the fact that you have all the particles in the same state at equals 0 is trivial. Also, classical gas will behave in this way. But if you have identical bosons, this can happen also at finite temperature. And so you will have a phase transition. And of course, in both the cases, whether you have bosons or fermions, so now this degeneracy parameter is on the order of 1. And this actually is the criterion for distinguish and quantifying the quantumness of your gas. Okay, before talking about Bose-Einstein condensation, that will be the topic of today, let me show you this behavior. So this quantum statistical behavior with an animation that can help you in remembering this concept and visualizing what happens in these 3 cases, so classical particles, bosons, and fermions. Here we are. So these 3 plots will show the occupancy of the energy levels in the case of a harmonic oscillator potential for the 3 distributions, so for a classical gas, for a gas of bosons, for a gas of fermions. And the 3 plots will all refer to the same quantity. So here I will plot this function n as a function of epsilon that I have written before. So the energy will be on the horizontal axis, the occupation number will be on the vertical axis in all the 3 graphs. So the 3 graphs will have different levels of zoom, so a different scale, to highlight the behavior both at large temperature and a small temperature, where the difference between bosons and fermions will be evident. So here I've considered a gas of 1000 particles, and the distance of the spacing between the levels is set to 1. So this gives the energy scale for the problem. And so let's play this movie, and let's look at the first plot on the left before. And so you see here that as you decrease the temperature, so we start with a temperature of 10,000, in units of the level spacing, you see that this distribution, of course, will shrink, and so the average energy will be reduced. And so you see that at large temperature, all the three distributions are basically undistinguishable, and so they all are well approximated by the Maxwell-Boltzmann distribution. But then, and you can see it in the central plot, so here they start to deviate considerably, and so for example, if you look at the red curve, you see that you have the formation of a Fermi gas. So this distribution deviates from the Maxwell-Boltzmann, and so at low temperature, you have this step-like function in which you have occupation of all the particles up to some, and let me stop the video, up to some Fermi energy. And this is what happens here. And this is, of course, very different from what happens in the case of bosons. And in the case of bosons, you have Bose-Einstein condensation. And so you have here, now in the plot on the right, you have the occupational ground state. So this is the Bose-Einstein condensate that is forming. And I'd like also, before playing the movie again, I would like also to invite you to look at the difference of these quantum statistics with respect to the classical one. Both in the case of fermions, because you see here that this dashed line is the Maxwell-Boltzmann, that is, of course, very different from the behavior of Fermi gas here. But also in the case of bosons, because in the case of bosons, the classical result is what is predicted by this dashed line, and so you completely miss the formation of the Bose-Einstein condensate, that is this peak in the occupation of the lowest energy in the system. So I will play the animation once again, and from the start to show how these distributions will start together, and at some point they will differentiate, and so you will have a quantum gas, and this happens when this number starts to be on the order of 1, and so you have the Fermi-Dirac and the Bose-Einstein condensation, and so here now the formation of Fermi gas and also the onset of Bose-Einstein condensation in the plot on the right. And the last thing, let me also invite you to look at these numbers now on this plot on the left. So here you have the chemical potential, and here you have the average energy per particle. So let's start considering the chemical potential, and you see here that the chemical potential for a classical gas is negative and large. I will come back to this point in a moment. And then as you decrease the temperature, it raises up. In the case of Bose-Einstein condensate, this tends to 0. In the case of a Fermi-Dirac distribution, this will tend to the Fermi energy. And let's also see what happens to the average energy per particle. And so this is interesting because now, when the gas is classical, for basically all the distributions, you get 1. So this example is for a one-dimensional harmonic oscillator. And so because of the equipartition theorem, so the average energy per particle is just kBT. And so this ratio, average energy divided by T, is just 1. But you see that you get different things for both for the Bose-Einstein gas and for the Fermi-Dirac gas. And so in the case of Bose-Einstein gas, so this value is lower than 1. In the case of Fermi-Dirac, it is larger than 1. And so let me also show you now this final plot in which basically I summarize these numbers as a function of temperature, and you see the different behaviors now. So chemical potential. So it starts with a very large and negative value in the case of classical gas, and when you reduce the temperature, you see that in the case of bosons, this will approach 0, and this basically marks the onset of Bose-Einstein condensation. In the case of fermions, it is instead positive, and it approaches the Fermi energy for your system. And in the plot on the right, you see this mean energy divided by the temperature, and 1 is what you expect from the equipartition theorem, and you see the deviation from that, again, at low temperature. Good. So we have reviewed the basics of quantum gases, and let's now specialize on the case of bosons. And so we will review the basics of Bose-Einstein condensation, and in particular we will only discuss the case of Bose-Einstein condensation in a harmonic trap. That is probably slightly different from what you have learned in previous courses, but this is highly relevant then for the experiments on Bose-Einstein condensation that I will show you later in this lecture. So let's see what Bose-Einstein condensation is. So let's reconsider the case of the ideal gas in the harmonic trap. And these are the equations that we have already written, and also with a density of states in the classical limit. What we have to do is to plug the Bose-Einstein statistics now. And Bose-Einstein condensation comes from a peculiarity of this expression. That is the presence of a -1. So this -1 makes this expression for the level occupancy pathological. In which sense? So differently from the Maxwell-Boltzmann and the Fermi-Dirac statistics, for which this n is positively defined for all the possible values of energy and chemical potential, you see that the Bose-Einstein statistics can become negative. So this n can be negative, and this is of course unphysical. So we need to require this expression, of course, to be larger than 0 for each possible values of the parameters. And for instance, the chemical potential will have to be a proper quantity in such a way to have n positive for all possible values of the energy. And so in the following we can consider, just to simplify our lives, so we can neglect the zero energy in the harmonic oscillator. So this is just a redefinition of a ground state energy that we will consider as zero. So this condition should hold for all possible states, and also for the ground state, of course. And if you write the occupation of the ground state, that is n0, this will be 1 divided by e to the minus beta u minus 1. Now, what happens? So, if we start from the classical limit, in which this quantity is much less than 1, and we already seen that this quantity is much less than 1 when mu, the chemical potential, is negative, because if the chemical potential is negative and large compared to the temperature, this quantity is much bigger than 1, and so all the fraction is a small number. If starting from this classical limit I want to make my gas more quantum, I need to increase the occupancy of the levels. For example, I can put more particles, and this will mean increasing the chemical potential. So if I increase the chemical potential, now this expression can become on the order of 1, and in particular you see that we have a maximum value for the chemical potential. And this is again because of this -1 at the denominator. The maximum value for the chemical potential is 0. So you see that when mu approaches 0, of course from the negative side, this exponential approaches 1 from the positive side, and so the occupation of the ground state will diverge. So this is Bose-Einstein condensation. And this divergence of the occupation of a ground state, that we can call n0, comes with a saturation of a population of all the excited states. So the Bose gas has this property of saturating the population that can be accepted by the excited states. And now I would like to show you. And so the approach is the same that you have also worked out when you have studied Bose-Einstein condensation in free space, so I will be very fast on this point. And so this is the calculation, and the calculation follows exactly what you already know. So one computes the total number of particles, and the total number of particles is composed by the occupation of the ground state plus the occupation of excited states. And you can call it NT, and this NT will be the thermal component of a gas. So we can divide our gas in the occupation of ground state, that is the Bose-Einstein condensate, plus the non-condensed fraction that will be given by the occupation of excited states. And typically, and a posteriori I can give you a justification for this, we can consider semi-classical approximation, in which basically we consider, we substitute the sum over the discrete states to an integral over a continuum of states in which we can use the density of states that we have reviewed in the last lecture. So this is exactly the same integrals that we have considered last time, but now we consider Bose-Einstein statistics. And in particular, so we have seen that Bose-Einstein condensation is important when this mu is approximately 0, and so in order to compute the occupation of a ground state, we can consider the case mu equals 0. And so if you plug mu equals 0 inside this expression, and then you write this integral basically in terms of this dimensionless variable x. Now this integral is can be written in terms of special functions, and these special functions are the gamma function and the zeta Riemann function. So this is just the definition of these quantities, and what you see at the bottom of the screen is the final result. And this term here at the bottom gives the saturation behavior of NT that I was commenting before. So if you fix the temperature of your system, so you see that this quantity has some value. So this quantity NT will depend only on the temperature of your system. So if now, at fixed temperature, you just add particles in your gas, so you increase N, so you understand that since you have already saturated the population of excited state, the only option to increase N is to increase the number of particles in the ground state. And this will be your Bose-Einstein condensation. So you start to form a macroscopic occupation of the particles in the ground state, and this happens because the number of particles in the excited states is already saturated by the maximum value that is allowed by the Bose-Einstein statistics. So in this sense, we speak of condensation, as it happens, for example, in the transition from a vapor to a liquid, because you reach the saturated vapor pressure of the excited states in some sense, and then you start to condense your particles in the liquid state that is the equivalent of what we call here the Bose-Einstein condensate. Okay, that's all. Then it's only a matter of rewriting this expression in a more convenient way, and so we can define a critical temperature. And the critical temperature, let me now scroll down the screen, is basically related to only the number of particles in the system, and also the properties of the confining potential, so in particular to the trapping frequency omega. Okay, and then you have this relation that is similar to what you already studied in the case of free space Bose-Einstein condensation, that basically describes the phase transition. So I can plot now this quantity as a function of temperature, and if you do that, this is what you get. So this is a plot of a condensed fraction as a function of a temperature, and so you see the phase transition here. So basically the occupation of a ground state is 0 or almost 0 until you reach Tc, and then below Tc you have this increase in the condensed fraction, a macroscopic occupancy of a ground state that of course reaches 1 at 0 temperature. And this is slightly different from what you studied in free space, because the critical exponent is different from what you have in free space, in which you have 3/2 instead of 3. But I mean, the idea is exactly the same. I promise you to comment on this semi-classical treatment. So the use of integral to approximate the sum over discrete states. And there is no problem with this approximation, and I can tell you why. Because in the experiments that I will show you in just a few minutes, we will consider clouds of cold atoms in which the number of particles is on the order of 10 to the 5, 10 to the 6. So if n is on the order of 10 to the 6, then Tc will be given by, so this is basically h bar omega, times n to the 1/3, n to the 1/3 is 10 to the 2. So basically all these physics of Bose-Einstein condensation happens at an energy scale that is given by 100 harmonic oscillator levels. So everything starts well above the energy spacing of the levels of harmonic oscillator. So I'll come up again. So basically this physics becomes important at an energy scale which corresponds to 100 of these levels. So basically it makes sense to approximate these discrete levels to a continuum of energy. So for all the practical applications, there is no problem in this semi-classical approximation of a discrete sum to an integral. Great. So now, before showing some experimental results, I would like to tell you one very last thing about the theoretical description of Bose-Einstein condensation of an ideal gas, in particular concerning the differences between what you have in the free space case to what you have in the harmonic trap case. And apart from critical exponents and the values for the critical temperature, what makes Bose-Einstein condensation in a trap different from Bose-Einstein condensation in free space is the fact that condensation occurs not only in momentum space, but also in position space. And this comes from the presence of a trapping. Because, of course, in free space, all the population will condense in the zero momentum state. In the case of a trap, will condense in the ground state of a trap. And if you consider a harmonic oscillator, you expect the wave function for the Bose-Einstein condensate to be the wave function of a ground state of a harmonic oscillator potential that is a Gaussian. So you expect the BC wave function to be a Gaussian like this with size, which is determined by the confining potential. And so we will see later and compare this prediction with what we get from the experiments. And let me finally give you some experimental numbers. So if we consider a gas of, let's say, 10 to the 6 atoms, and the trapping frequency that is on the order of 100 Hertz, that are typical numbers for these experiments, you find that the critical temperature for Bose-Einstein condensation, let me give you the temperature in real units, so in Kelvin, will be h bar omega divided by Boltzmann constant times n to the 1/3. And so if I convert 100 Hertz in temperature units, so with the Planck constant and the Boltzmann constant, this will be approximately 5 nanokelvin times the number of atoms to the 1/3, that is 100. And so the critical temperature is on the order of 500 nanokelvin. And so it seems in the range of the temperatures that we can achieve with evaporative cooling. That is the technique that we were discussing in the last lecture. And so what do you need to get a BC? In a few words, you need everything that we have studied in the first 2 months of this course. So these are the sequences of a typical BC experiment. So everything starts with laser cooling. And with laser cooling, you can get cold gases, so in the tens of microkelvin without spending too much effort. But we know that the densities are pretty limited. So the gas is very dilute, and so the degeneracy parameter is typically small, 10 to minus 8. So these numbers are very qualitative. So of course it depends on the specific atom you're considering and specific setup. So these are just some orders of magnitude. And in particular, these are for typical values for a rubidium experiment. Good. So in order to do more, we need to perform evaporative cooling. But for evaporative cooling, you need first to trap the atoms in a conservative trap. And so you need a magnetic or optical dipole trap. That, however, requires laser cooling before. So after laser cooling, you have the trapping phase. So as soon as you trap atoms, you almost immediately gain in the density, because you can confine the atoms in a tight region of space. And this comes at a price. Typically, you have also a heating. And this because you have a gas, you compress this gas, and so you have, in a compression, you always have some form of heating. And so you have basically something on the order of hundreds of microkelvin, but you gain already something in phase space density, and so you have 10 to the minus 6, but still the gas is very classical. So if you want to make it more quantum, you need to perform evaporative cooling. And you have seen last time how evaporative cooling is efficient. And so by throwing away 99 or 99.9% of the atoms, at the end the remaining atoms are cold and dense. So you can get these regimes of hundreds of nanokelvin with 10 to the 13 atom per cubic centimeter, where the phase space density is on the order of 1. And so this cycle takes something like half a minute, and that is shared between the laser cooling procedure and the evaporative cooling procedure. So the laser cooling procedure takes some time because you need to start with a good number of atoms, and so you are collecting these atoms from the atomic beam, and so it needs some time because of a flux of initial atoms that you have available in the experiment. And then also evaporative cooling takes time, and we have reviewed that in the last lecture because you need interactions between the atoms to reestablish the thermal equilibrium after the forced evaporation. Then you spend half a minute of your life, but then you have a nice Bose-Einstein condensate that you can make experiments with. But how we can check that you have a Bose-Einstein condensate? So what is the detection technique that we can use to check that indeed we have this physics that we have reviewed in the first part of this lecture? So the most common technique for detecting cold atoms is imaging. And we have seen some applications of this approach already. And so let's see what kind of imaging we can perform and what is the signal that you can look at. And the most common detection technique is absorption imaging. And I've already shown this figure to you, and here you have atoms that are illuminated by an imaging laser beam, and the shadow that your atoms leave on the laser beam because of absorption of light is imaged by the CCD camera. So the CCD camera detects a dark area, and this dark area corresponds to the shape of the atoms that have absorbed the light. And usually I have also discussed that this technique is performed in a time of flight fashion. So you basically have your cloud of atoms, and then you switch off the trap, here the magnetic trap or the optical dipole trap, so the atoms will fall and they expand. And so from this kind of measurement, so you can reconstruct easily the momentum distribution. So not really the real space distribution, but the distribution in momentum space. And so if we do this after the evaporative cooling, and in particular, if we block the evaporative cooling at different final temperatures, this is what you get. So in the upper row, you see these absorption images as they are detected from the CCD. So where basically here black means no absorption, and red means medium absorption, and yellow means large absorption. While in the row below, you see some cross-sections with a density which is plotted as a function of position, and this corresponds to an integration of these images along the vertical direction. And so what do you see here? You see that when you cool your gas more, at some point you have a significant increase of density. So you have a discontinuity in the increase of density, and so you have the formation of this core. This core is the Bose-Einstein condensate that in this intermediate picture forms on top of a non-condensed cloud. So here in the central figure, so you see that this is the condensed fraction that we have called N0 in the previous discussion, while here you have the atoms that form the thermal component of a cloud. And then you cool more, and so the condensed fraction increases, and to the level at which we do not see the thermal component anymore. So basically here you have just a pure Bose-Einstein condensate. So here the condensed fraction is approaching 1, and so your atomic gas is almost completely Bose-Einstein condensed. So here you see quite clearly this transition, this Bose-Einstein condensation phase transition, and there is a lot to be said about these pictures. And if you look carefully at these images, you will note two things, in addition to this discontinuity that we have already commented. First, you see that the shape of the density distribution changes. And so here you have a function that is well fitted by a Gaussian function. When the cloud is partially condensed, of course you have a situation in which you have a condensed fraction and a thermal component, and so you expect, and indeed you can fit it with a bimodal function. So a distribution that is made by two different components. One that describes the thermal component, so the non-condensed fraction, and one that describes the condensed part. In the last plot of a pure Bose-Einstein condensate, you see that the fitting function is not a Gaussian. It's not what you expected from the theory that you have developed before. We will see why later. But for the moment, let me just tell you that the best function to fit this density profile is an inverted parabola. Or we can call it also Thomas Fermi function. And we cannot explain that on the basis of what we have reviewed so far. I will tell you why. But we can clearly see it. So we can clearly see it also from the images. So while the thermal cloud is a smooth function, which density goes to 0 rather smoothly, in the Bose-Einstein condensed case, you have sharp boundaries. So you don't have the tails of a Gaussian. So here, the density goes to 0 almost discontinuously. So you have sharp edges of your Bose-Einstein condensate. And you have to understand why, and we will. There is another point to which I would like to draw your attention, that we will also explain later. While in the case of a thermal cloud, you observe a shape that is rather isotropic. So you have a very good rotational symmetry. In the case of a Bose-Einstein condensate, instead, you see that the shape of the Bose-Einstein condensate is not spherical. So it is rather elongated along one direction. Much more than what you have in the case of a thermal cloud. So here we have something that is mostly spherical. Here you have something that is, let me say, with just these simple words, elongated. And later I will explain you everything about the shape of this BC. Before that, however, let me review what you measure here in the case of thermal cloud and why it is a Gaussian and why you have this spherical symmetry. And actually there is not much to say for the thermal cloud because we already know how to handle that. So when we discuss laser cooling, we have commented that in this time of flight imaging technique, basically what you observe is the momentum distribution. So if you wait a long time, and so you allow for momentum to be converted into position, so what you measure, so the density after time of flight, is basically corresponds to the momentum distribution that you had in the trap. And so if you have a thermal gas, so a gas that is in thermal equilibrium and to a very large extent, so the part of a gas which is not condensed is very well approximated with a Maxwell-Boltzmann distribution. And so you can take the Maxwell-Boltzmann distribution, and that describes the momentum distribution of a non-condensed cloud, of a part of a cloud that behaves classically in some sense. So this is a Gaussian, and the width of this Gaussian is related to temperature. And so from these images, so from the thermal cloud, we can extract the temperature of a gas. And also, of course, this distribution is spherically symmetric because the temperature in a thermalized gas is the same, whatever is the axis, and so all the cuts along x, y, and z direction have the same width. So let's go back to the images. So this is our Gaussian function, and okay, so here don't look at these modulations here on the top. These are just because of some artifacts in the imaging, so these are not important. But apart from what happens on the top, everything is very well fitted with a Gaussian, and the Gaussian fit will also give you the value of the temperature. And the same applies also in the case of a partially condensed cloud. The fit of the external part of a cloud with a Gaussian function will give you the temperature. So this external component of your density distribution. So let's now take a break. And so let's see some experiments. So let's visit a lab. So you know that in this period we have restarted our research activities, and so we are trying now to make our lab running again. And so I've asked two distinguished colleagues of mine that are working in the lab now to record a video. This was just taken 2 days ago. So in other periods, I would have taken you to the labs, but I cannot, and so I can show you now this video. And so you will see how to make a BC. So you will see the experimental setup. You will see the images of atoms that are showing on the screen of a computer that we use to control the experiment. And so you can see this phase transition that is observed in real time in the lab. Okay, so let's connect with the physics department and enjoy this virtual lab visit.
Hey everyone, I'm Daniele Tusi. I'm a PhD student in the Terbium lab. Since real lab tours are not allowed due to the quarantine, we are going to organize a virtual lab tour. During this tour, I will be your cameraman and Giacomo will be your guide.
Hello everyone. Come in, please.
Mamma Giacomo, che capelli!
Daniele, che vuoi? Manco io vado dal barbiere, The first thing that I would like to show you is the experimental setup that is hidden behind these black panels here. So let me open them for you so that you can see what is hidden inside. Okay, so in this big aluminum box here, there is an oven, an atomic oven, that is the main source of atoms in the system. All the atoms come from this oven here with a very high speed. So, as a first thing, it is necessary to slow them down. And this is achieved using this Siemens blower that you can see here. Daniele, can you fit the camera in? Okay, perfect. You see this set of increasing coils. These are the coils forming the Siemens slower that have bigger and bigger diameters, so that as the atoms travel through the Siemens slower, their change of speed can be compensated by a change in the intensity of the magnetic field. After the Siemens law, the atoms are then collected in the magneto-optical trap that is instead in this other side of the setup. This chamber that you see here is where the atoms finish after traveling through the Siemens law. They stop at the center of this chamber here, where all these green laser beams that I hope you can see here on the desk, they are coming from all directions, from 6 directions in space, and all of them crosses in the center of that chamber, of that vacuum chamber. In the same place, the atoms are also trapped after being pulled in the magneto-optical trap in an optical dipole trap, where the evaporation is then performed. So I want to show you now how the experimental cycle works. So the first stage of the cycle is represented by the magneto-optical trap. On the screen you see this green trace that represents the fluorescence emitted by the atoms collected in the moth, that, as you can see, increases in time due to the fact that we have more and more atoms into the magneto-optical trap. At a certain point then the atoms are transferred from the magneto-optical trap that is turned off into a pair of dipole traps, optical dipole traps, that we use to perform the evaporation. In particular, you can see this exponential ramp here on the red trace that represents the final evaporation in the optical dipole trap from a very high value of power, of laser power here, and that corresponds to a very high value of trapping depth, to a lower value of laser power, that means a lower value of the trapping depth. It is not easy to obtain a Bose-Einstein condensate at the end of the experimental cycle that I just showed you, because the type of gas that you obtain strongly depends on the details of the ramp, for example the speed and the final trapping value. In case, for instance, your ramp is too fast, atoms do not have time to thermalize. On the other hand, if the final trapping value is too high, the average temperature of the gas will be too high, and we will have a thermal gas instead of a Bose-Einstein condensate, as we have in this experimental image here. As you can see, this distribution is purely Gaussian, as it is demonstrated from these fits here that are the red line that perfectly superimposes with the experimental image that is represented by the blue line. So the thermal gas that we have in this image is not good at all. We want to reach the quantum degeneracy. We want to have a Bose-Einstein condensate. So in order to do this, let's change the final trapping value. Let's put a smaller value so we have a shallower trap, and let's see what happens. So this is the image that we obtain at the end of a cycle with a slightly lower final trapping value. What we have here is a gas that is a mixture of a Bose-Einstein condensed part at the center of the trap in a thermal bath with a Gaussian distribution around. As you can see, in this case, we can no longer use a Gaussian fit to describe the image. We need something else, but at the same time we cannot even use a Thomas Fermi fit, that is that of a pure Bose-Einstein condensate, to describe this image, because you see here the fit is not getting the details of the image that we have. What we need is a function that is a mixture of that is a sum of a thermal part and a Bose-Einstein condensed part. That is where, okay, it's here. You see, with this bimodal fit, we can catch all the details of the condensed part and of the thermal tails at the external part of the trap. So now it is a bit better. We have a part of the gas that is condensed, we have a bit of Bose-Einstein condensate, but we want more. We want to get rid of the thermal part and obtain a pure Bose-Einstein condensate. So what we do now is to lower even further the final trapping depth, and let's see what happens. Okay, this is very, very good. This is very, very good. Now, as you can see here from the image, we no longer have any kind of thermal gas around. We only have this spot here, and that is the Bose-Einstein condensate. As you can see, now I can easily use a Thomas Fermi fit that perfectly matches the experimental figure that we have here.
Good job, guys. So now we know how to make a BC, we know how to see it, but we still have to explain its shape. But we'll do it in the next video. Bye-bye.